Thank you. RadiaSoft, we're a small company in Boulder, Colorado. There are about 17 of us right now, and we're growing. We were founded in 2013, and we developed software for particle physics simulation. And so we do a lot of ray tracing and particle tracking, a lot of EM calculations. And so it's sort of out of the scope of what COMSOL does, but I'm going to talk to you today about how we incorporate and use the multiphysics aspect of COMSOL to sort of bring our simulations together. The project I'm talking about today is in collaboration with Argonne National Laboratory. Argonne is located about an hour outside of Chicago. It houses the Advanced Photon Source Synchrotron facility. Can I ask real quickly how many people are familiar with synchrotron light sources? Oh, wonderful. Okay. I was not sure. Okay, so it is a type of accelerator. It's not the most popular kind of collider, but I'll give some background about it. Okay, so all right. I'll go through some background, and I'll talk about synchrotron light sources. I'll go through a typical simulation. I'm going to be showing you some models that I've created for vacuum chambers in the light source that house the electron beam that go through the ring. And then I'll talk about GUI development using COMSOL's application builder. That's something I've done several times out of complex underlying simulations. GUI is graphical user interface, just in case. I'll show you some screenshots of the GUI, go through some of the features, and talk about our ongoing work. This is a 2, maybe going on 3-year collaboration right now, and so okay. Should give it a second here. Right, so you see the yellow, you've got an electron beam going around a ring. That is the APS, or Advanced Photon Source. It's a little over 1 kilometer in circumference. It keeps this electron beam going in a circle with bending magnets. There are quadrupole magnets, sextupole magnets that focus the beam. That red synchrotron radiation coming off of it, those are very high energy X-rays. And as a charged particle moves in a magnetic field, it's going to emit X-rays as a form of energy loss, right? So you also have RF cavities inside of the ring to bring the energy back, and it's called a storage ring because even though it's losing all of this energy, you're building it back by throwing it through RF cavities, and so it can house an electron beam for 6 hours, 8 hours, maybe even a day. And those little jagged pieces that you see along the ring, each of those is a unique beamline tailored to a certain type of experiment, right? And so people in materials science, chemistry, biology, they'll run different types of experiments on each of those beamlines. I think the APS itself, has around 32 beamlines, and they run all sorts of experiments. These beamline elements are optical elements that will tailor the beam to a specific experiment. Okay. Here's a cross section of the storage ring. You can see where those red arrows are coming out. Those are beamlines. Today I'm going to be talking about the vacuum chambers that house the electron beam that goes around the ring, right? So I have done plenty of simulation for beamlines, high heat load optics, but today I will be talking about radiation incident on these vacuum chambers. Okay, and so a little bit of motivation. The Advanced Photon Source is undergoing an upgrade currently, and there are a handful of other machines in the States and around the world that are also going through upgrades. There are several machines that have been newly commissioned, so new machines are popping up China is making a new collider and a new synchrotron. And so we're trying to develop this simulation software to aid in the design of vacuum chambers for these machines. Okay, so there are a few plots here. If you look at the bottom left, this beam size, that is what the electron beam cross section looks like today at the APS. Has a large horizontal emittance and a very low vertical emittance. You can see this brightness plot on the top right shows APS today. Brightness is essentially intensity. It's sort of a figure of merit for synchrotron light sources. You can say, okay, this machine is this bright, and this one is, less bright. You want brightness. And so it's essentially intensity. It's sort of like a phase space intensity, but you can think about it as number of photons per second per unit area angle, right? And so this will make a bit more sense, hopefully, as I progress. But finally, I just want you to look at this vacuum chamber cross section. So I showed you in the storage ring, a cross section of the storage ring. This is a cross section of the vacuum chambers that house that electron beam. Okay, so that's the current chamber. It's about 200 millimeters across. Okay, and so the upgrade is going to reduce that horizontal emittance. And it's beyond the scope of this talk to explain how they do that. But the most important part is that the magnets will be getting closer together. We need smaller vacuum chambers. There's not enough room for them. So not only do we have a much brighter beam and higher intensity X-rays, our vacuum chambers need to be smaller. And so all of the design challenges and all of the physics are seriously amplified, right? We'll get very high heat loads, in addition to lots of other headache challenges. And you can see the APS upgrade, we'll see about maybe 2 orders of magnitude increase in brightness intensity. Okay. And then here are a couple 3D models. You can see the current vacuum chamber, looks like this, and those little holes are for water cooling. All right. So the state of accelerator simulation today, actually at RadiaSoft, we helped develop a lot of these codes. There are tons of different codes written by maybe 2 or 3 or 5 people, and they're very specialized. You've got particle tracking, ray tracing, waveform propagation, molecular flow codes, and they're all typically very messy and undocumented. So while we do help develop them, they're a huge pain, honestly. And sometimes the people who made them aren't around, or they're not being developed any longer. It's really a bit of a mess. These codes that are next to this confused guy's head are just like 6 out of 500, maybe, right? And so not only are they very difficult to learn, there's data incompatibility. So you can't go back and forth between, for instance, your ray tracing simulation and then into your molecular flow simulation. Okay, so this is where we use COMSOL Multiphysics, and it's fantastic for that. Not only can we develop these simulations, I can do ray tracing inside of COMSOL. I can do a thermal analysis, structural analysis, desorption, outgassing with molecular flow. I really exploit a lot of COMSOL modules, especially for this project, right? And then I use the application builder to put these models into a GUI, a graphical user interface for scientists and engineers who maybe don't know COMSOL or don't know these codes to access it on our cloud-based servers using the COMSOL Server license, which is fantastic. They don't have to have a license, and they can use our servers, which have essentially unlimited RAM and cores, and it works out very nicely. Okay, so to give you an idea of everything that we are modeling in this project, if you start at the top of this workflow, I know it's a bit messy. You start out with the geometry. We can do particle beam tracking. There's a charged particle tracing module in COMSOL, which is useful if you really want an accurate model of, say, many charged particles. For now, I have an analytic formulation that will tell me the ideal orbit. Then I use the ray tracing model to say, okay, you've got this charged particle beam going through the storage ring. What does the radiation look like that's emitted from that beam? We can do reflection. That's very easy. We get a heat load, then we do a thermal analysis and a structural analysis. I will talk about one of the guys in red later. The other is very complicated. Okay, feel free to ask me about it after. Okay, so here's just an example of using this ray optics module in COMSOL to do ray tracing. Typically, we would model a large section of electron beam trajectory. This is just like maybe 10 millimeters of propagation and 10 millimeters worth of radiation. And you can see it's incident on the side of the vacuum chamber. And in blue, you have some of the reflected rays that were not absorbed. So in this step, I can get a heat load. From there, I can do a thermal analysis. In this case, I've just done natural convection. In a more sophisticated model, I will draw in water cooling, as I've done in the past. And then from there, we can use the structural mechanics module to do a structural analysis. Okay, and this is an example that is massively overly constrained, but it shows you where the rays are coming in, what's happening fairly clearly. Okay, yeah, so I wanted to take this slide to let you know exactly our process at RadiaSoft and what we're doing now with several DOE labs and private customers. So we will develop this complex simulation, put this GUI together that has the relevant inputs and outputs, and then we'll give them access to it on our server. And so far, that's going very nicely for us, and we're looking to keep developing more of these GUIs and simulations. Okay. So this is the application builder interface, which is very nice interface. Like on the top right, I have this sort of nauseating video of me putting together an application from a year or so ago. So you can see that I don't know how many people have used it. You can drag and drop lots of different model objects onto your canvas. So you can go into this model that you've made and you can say, okay, I want this result, or I want a drop-down menu, and it gives me choices. You can just pull them down into the canvas, and that's very simple. If you want to add a level of sophistication that's often required, they have a built-in Java development environment. I use that very often, not only in creating the underlying models, implementing my own algorithms, but actually creating the GUIs themselves. Okay, and COMSOL has a very extensive API, but they make it easy to access that by recording methods. So you can do this, excuse me. So you can go, you can click record method, go into your underlying model, run a handful of procedures, say run a calculation, get the result, change an input parameter, stop recording the method, and it will spit out that Java code for you, which is amazing. It's been very nice to use. Here's some snapshots for the GUI that I have under development for this simulation. You can see where you define your electron beam source, right? You can give it an arc length or a bending radius. You define the energy of the beam, the strength of your dipole magnet, where it ends, where it starts. Choose the size of the mesh. Right, here's a plot. It shows a structural analysis. Gives you a displacement. Shows you what the mesh looks like. It's probably overkill to include the mesh. Right, here's an iteration of the GUI that did a live update of the rays that you trace, and it shows you the energy and power distribution of those rays. The synchrotron radiation power distribution is fairly complicated, especially as it progresses along an electron trajectory. And so it's often nice to plot what that distribution likes at various points in the simulation. Right? It's a snapshot with a temperature plot and some incident rays. Right? And you can choose how many rays you'd like to release. I think in the newest version of the GUI, you can choose how many cores you want to use on our server, which is really nice. You can run many simultaneous jobs, speed things up. Okay, and so right now we're working on something called photon stimulated desorption. Most of you are probably familiar with the desorption process. Not only does the synchrotron radiation heat the material and you have thermal desorption, you get these ions kicked out, but you also have this atomic excitation. Photons come out and they kick out electrons. The problem with having all this contaminant gas is that it kills the vacuum. And the importance of having a vacuum with a relativistic electron beam going through it is that the beam will die, right? You need this guy to be in a vacuum. And so we are currently modeling outgassing with the molecular flow module, and we're putting pumps into our geometries with outgassing to see how fast we need to pump out these gases in order to maintain the beam lifetime. Right, and that's a difficult problem. I've talked to a handful of people who have been trying to solve this for a long time. It's largely done with experiment now, and so I think we're just starting to model this sort of thing, right? And then there's just continued development of the GUIs. At RadiaSoft, I have currently been the only COMSOL engineer until recently. We recently hired someone who will begin working with me on this. It is quite a bit of work to develop all of the underlying simulations and develop the GUIs, right? And so you have to sort of go back and forth, right? And we're trying to build a user base for the applications and relevant users so that they can give us feedback. When I make a GUI, I don't necessarily know what everyone is going to want, right? And so it's very valuable to have this. There's a screenshot on the bottom right of our COMSOL server. This is where you would access the applications from your web browser. Okay, and you can try it yourself. So you can go to repo.com/COMSOL and request a login, and you can test the GUIs that I've made. I believe you can test 2 of them that are DOE projects, and they're specialized. But feel free to email me any questions. I'm happy to hear feedback. It'd be fantastic. Thank you.